Hello, my name is Greg Althouse. I'm CTO at RackN. In this video, Everything DigitalRebar in 30 minutes, we will explore the open source project DigitalRebar. RackN sponsors the open source project and additionally provides a supported release of DigitalRebar called RackN Enterprise that includes an advanced dashboard and proprietary roles for non-open sourced technologies. For example, some of these roles deploy a software-defined networking layer or provide a hardware burn-in and decommissioning lifecycle for nodes. But more on roles later. At this point, I'm going to start some virtual machines to simulate our bare metal environment. Let's see. Let's make sure these get started. And they go through a Pixie boot cycle. Yay. While these systems boot, where'd my mouse go? There it is. What is DigitalRebar? DigitalRebar is a hybrid automation platform that normalizes heterogeneous infrastructure so differences between infrastructure platforms can be isolated, allowing automation to run anywhere. Whoa, whoa, whoa. That's a full mouthful. Let's decompose that. First, hybrid automation platform. DigitalRebar manages physical hardware, bare metal nodes, as well as cloud-based VMs and containers. These hybrid environments need a platform to provide coordinated automation. Second, normalized heterogeneous infrastructure. DigitalRebar provides an abstraction layer to handle not only differences between cloud and bare metal, but between multiple types of vendors of bare metal and multiple cloud providers. Finally, all of this is to provide a consistent automation environment. And by automation, we don't necessarily mean our specific roles, which we do, but also the ability for the user to add automation based upon the tooling that is specific to their needs. With DigitalRebar, we've tried to enable Ansible, Chef, Puppet, SaltStack, and even plain old scripts as components to the automation system. At this point, let's dive into the demo. I'm going to focus on showing concepts through the UI, but realize that the UI only uses our RESTful JSON API. We also have a CLI and Go-based libraries that can be used to drive DigitalRebar programmatically as well. So nodes, let's start with nodes. At the heart of DigitalRebar are nodes. These can be bare metal, as shown here, or cloud VMs. DigitalRebar maintains attributes about nodes. So let's go look at some attributes. So these are my VMs being discovered, and they have roles, what we call node roles, running on the system, gathering information. And as they run, we'll gather more information into attributes. Now, an attribute is just a kind of key value store, of which the values can be Booleans or strings or maps, but in the end, they're the descriptors of what the node will be. And you can see we'll gather things like whether IPMI is available, what type of CPUs the system has, how many, what disks are available. And this node's in the middle of still being discovered. As you see, its node roles are being run and being processed. And as part of that, each node gets built and discovered as it comes up. And so in this case, we've Pixie booted a discovery image. This discovery image has all the tools needed for that. It's a CentOS 7.2 RAM-only image. And as the node comes up, we run our roles, which are these circles, to gather various information. And in this case, it can be just system inventory. It can be network inventory, like we run LLDP to figure out what switches the systems might be configured to. And the process will also do things like try and discover if there's an IPMI control system, like a BMC, an iDRAC, or an ILO. We'll also look to see if there's a RAID subsystem that we can manage, and we'll run tools to discover that. We'll also look for BIOS as well. All those steps of the process lead to filling out these attributes. So I'm going to refresh this and see if we have a few more. In this case, since it's a virtual machine, I don't expect to see the hardware parts, though we should be able to see things like the how many CPUs and disks and such as that. as my system is weighted down a little bit. Slowly coming back. Once this image is run, as you can see, we've started to pick up the virtual BIOS, and all these attributes become available to the nodes to drive future configuration, either OS to install, what systems it could have, even pick up RAID and all that stuff. Now, to get these nodes discovered, DigitalRebar provides a data center's amount of services. Any service that is needed, DigitalRebar can provide, or it can be configured to use an external instance of that service. So a service in this case is things like DNS or DHCP or NTP, a logging service, all those kind of things. So maybe we should take a quick look at what the rebar architecture is. Now, what I'm going to show you is a compose of what our system is. DigitalRebar is provided as an admin node. In that admin node, we run Docker, and we use Docker Compose to manage a set of containers. In these containers, we run basically microservices that are orchestrated to provide all the data center services we need, in addition to our API services and our provisioner services, and all those things are in these containers. So the first container we have is Console. Console provides two things for us. It provides a way for all the services to register and figure out where they are, as well as a persistent key value store to store kind of ephemeral information that we want to be available even if a certain container were to die, but it's not necessarily considered long-running information. The next set of services are our kind of data center services. That's DNS, NTP, DHCP, a logging service, and our provisioner. All of those represent kind of things you need in your data center to provide bare metal provisioning as well as operations of applications on top of those bare metal systems. Now, every single one of those services can be replaced or told to use an external service. In the case of DHCP, we can use an external one to use your own IPAM. The only requirement is that the DHCP next boot would point to our provisioner. The DNS subsystem, we can use it. It runs a bind service inside of its container, or it can be configured as to just reference an upstream DNS server. In addition to providing DNS, it also provides an update capability such that DigitalRebar can update DNS entries in an upstream DNS, and that works through either calling NSUpdate directly, or we do direct integration with PowerDNS, and we can manage our own bind service. We run a logging service, which is basically a syslog endpoint, and we set the nodes to forward logs to there. NTP is obvious. We kind of synchronize time across all the nodes. And then we provide our provisioner, which provides a set of boot environments. Think of it as an advanced cobbler that can be used and customized to provide multiple boot environments as well as serve files to the nodes. The next set of kind of containers are kind of our provider services, and Cloud Wrap is that one. It allows us to talk to the cloud services to provision nodes and decommission nodes from cloud instances. The Goyardi container, we run a Chef service. A lot of our roles are provided by Chef cookbooks, and we run a stripped down Chef server that can serve those cookbooks to the nodes. We also have a web proxy that allows nodes to not require internet access, but still access installation and media and other things in the internet through the admin node. It also acts as a cache to speed up downloads. In the next three containers, or four really, is the rule engine. And actually, let's start with the Rebar API. Rebar API container provides the core framework of APIs that allow you to manage nodes, bring up systems, and all of that stuff. The rule engine represents an event responding system such that the Rebar API container can throw off events for everything that's going on. And the rule engine acts as a dynamic processor of that so that we can do advanced workflows like automatic provisioning, automatic decommissioning, those kind of things can be provided through the rule engine. The last two containers provide our access control and security. We have a Trust Me container. That's our PKI infrastructure. We have a RESTful API-based system that will do multiple root CA management. And so each container gets a signed key so that all the containers, to talk to a container, you have to have a signed certificate from Trust Me. And then that also provides an API for the rest of DigitalRebar going forward so that if systems need their own CA certificate chains, Trust Me can provide that and inject those into those systems. And then Rev Proxy acts as the control entry point for all of those systems and provides our multi-tenancy system. So we have an RBAC user login tenant system to allow multi-tenancy that allows controlled access to all the resources, and the Rev Proxy fronts that identity system, and it can be ours or we have it implemented as a pluggable system. Currently there's an Okta integration, but it's pluggable to add additional ones as needed going forward. And at this point, so those are kind of our containers. They're provided as services. The containers were chosen so that we could provide faster updates. We can restart the services. The system will continue to function. All of this is also backed by a set of scripts that allow you to back up a system, to restore a system from backup, and then we can also update the system through orchestrating container restarts. The next roadmap item in the future is full HA, which at this point revolves around making the Postgres database HA capable. But that's an immediate roadmap item. At this point, we'll go back and you can see these services as rendered through our UI. So in this case, I can show my DHCP subnet. I can see my nodes that have been booted. They've been assigned addresses through our network management system. And we'll talk about networks in a little bit. Notice they've been given bound addresses. We can see their leases. We can see their options. Again, this is a RESTful API, and so we can go see the, let's see, this one. We can go and see the actual data through the system actually directly queried. And then we also have our DNS subsystem. We create DNS entries based upon the nodes and the networks they're in. There's a rule system, a set of filter rules that allow you to dynamically create names and entries in the DNS subsystem across multiple zones, including reverse pointers, to based upon nodes' properties and attributes. So if it's in a network that you want to have a name, you can create that name. Right now, the default naming is based upon the MAC we booted from, but it also could be based upon the node's ID or other properties. And nodes can be renamed afterwards as well. Then there's our provisioner. The provisioner manages what a node's going to boot into. So in this case, we can see they've booted into Sledgehammer, and there's parameters that we're injecting into those boot environments. But we have lots of boot environments. Boot environments are the Sledgehammer images that we boot. We have a local one to install or to basically tell it to boot to local disk. In addition, we have our install images, and an install template is a ISO that's been exploded into the provisioner environment, so its images, so its files can be served, and then a set of templates that will build out and allow you to boot. So in this case, we have our default boot system so that we can handle both, or actually all three of a UEFI boot, as well as a couple of versions of Pixie boots. And then we have the templates. Now all these templates are built per machine as needed when the machine boots. That way we can build a very customized image per machine. And then those templates are just what they sound like, templates that can be exploded. So for example, in this case, we have a template that represents the Kickstart install file for CentOS 7. And you can see we have ways to inject attributes based upon attributes discovered on the node, as well as system attributes. So like that proxy server I mentioned earlier, we can inject it as needed. The powerful thing about this is you're not limited to our predefined boot environments. You can create your own ones. We've had some customers that have said, well, that's great, but what I really need is a software-defined RAID environment And that's not standard, so can we change that? So sure, you can either customize this template directly, or you can create a whole copy of the boot environment, customize your template, put in the right configuration that you need for your system, and then point the nodes to boot and install that template. So that's kind of the provisioner and how the provisioner operates. Now, at this point, we've kind of shown all the endpoints. Our rules engine also has an endpoint. It's kind of a work in progress to make this more visual. But the idea here is that it's a dynamic set of rules that, based upon events, like this one says, if a node moves among the deployments, which we'll talk about, match some values from that event, and based upon a test of that, do some actions. Those rules can be dynamically added or removed. That allows us to do all sorts of things like automatically moving nodes. In one case, we've seen customers that want to say, okay, if you detect a node that comes in with 20 disks, that's a storage node, provision it as a storage system, put it in this deployment. That kind of workflow can be handled through these dynamic rules. Now, I've kind of shown you all the stuff about a bare metal system and how we move with that. The nodes will show up, they get put in a system deployment. Click on my deployment, on my system deployment, and they get stored there for use later. That allows us to find the nodes in the system before we actually try and assign them. But if we're talking about cloud instances, then we need to add providers. So I'm going to run a little script that I've kind of wrapped quick around my RESTful API, and I'm going to add some providers to the system. A provider just represents an access point to our cloud. In this case, I'm going to add a Google one, a Packet one, and an Amazon one. And this represents a set of credentials and, in some cases, a region or account that we need to add machines to DigitalRebar. So with these in place, I can now look at them and add systems in place. So let me look at the Amazon one, for example. Maybe reload. Do it add? Oh, it's still in process. We'll look at the Google one. So here's my Google provider. I have my project I want to operate in. I have my JSON key file. I can even add hints so that when I create a node, I get a certain type. This could include a default image, a default size of VM that I want to start up. All those are kind of consumed in this default provider. Now they can be overridden on the create call, but that's how we provide that. Now you notice there's one at the top called Metal. Well, our Metal provider does just that. It operates and provides the system needed to actually manage bare metal nodes. So now I have my Amazon provider and I can see it has similar. But in this case, like for Amazon, I need to specify the region because everything is kind of region based. Same set. Now, at this point, I've kind of talked about providers, I've got nodes. At this point, let's talk about deploying a workload. In this case, I'm going to deploy a Kubernetes workload. Actually, I'm going to deploy 3 Kubernetes workloads. And to do that, I'm going to use our wizard. And we can do this through a more directed process, but we'll start with this to kind of get through the idea. In this case, I'm going to create an Amazon flannel-based Kubernetes install. So I'm going to create a deployment. Deployment is just a holder of nodes. It's a kind of way to group nodes that are going to have a functionality. In this case, I'm going to auto commit, which says make it happen when I'm done. If I didn't do that, I could choose. So I'm going to use my Amazon provider, and I could name my cluster. I'll just leave that. And I can then tweak some common parameters. I could change Kubernetes version as I need. And then at this point, I get to choose how my systems lay out. I get to choose my networking. So I'm going to choose Flannel. It works better in the clouds. I could have chosen no SDN as a networking layer, which is very helpful for bare metal systems that have a common L2 domain. And then I get to choose whether I want control or workers. I could choose 3 control nodes to do an HA kind of deployment. In this case, I'm just going to do a simple bring up with my workers. At this point, I choose next. I get to see the JSON that's going to be committed. I could save this and replay it to recreate environment, or I could tweak slight parameters like a name if I wanted to create a new instance of it. This allows me to replay that through the system. And then I can say go, and it's going to commit it. Now what it's going to do at this point is it's going to create some VMs in Amazon and then start driving the installation of Kubernetes on that. Now, in this case, I'll start with that, and I'll go to my Amazon console, and I can see my nodes beginning to spin up. If it refreshes. Let's see. So there's my nodes starting to come up. I already had one running in the system, and so they're slowly beginning to start up. In this case, I can see my wizard running. And with DigitalRebar, I can run not just one instance of Kubernetes, but I can provide multiple instances based upon my need, and using the deployments, I'll get separation. Now, when this is done, I'll start up my next one. The goal of DigitalRebar is to normalize the various levels of the system so that the next system doesn't have to worry about what's actually going on. So in this case, the Kubernetes deployment I've started on Amazon, and slowly getting progress on, should, that same deployment, I should be able to use to install my physical machines. So I can say local flannel K8s. And in this case, instead of saying, give me a cloud one, I'm going to say use my existing nodes, and I'll choose an OS to install. And then I get the same set of options, but in this case, it says, oh, you only have 2 nodes, and I'm like, okay, well, let's go with that same set of options. And now I get a slightly different one because I have specified nodes and can then say deploy it. Now, when I deploy this instance, it will move my nodes into a new deployment, and then it should start the nodes through a booting process to reinstall them to have an image because they don't have an OS yet. So the OS install process should occur, and we should start seeing them move forward. Checking the Amazon nodes to see if they finished coming up as well. Yeah, they're all there. They're finishing their initialization. Now this is running, so hopefully my VMs should start rebooting shortly. Now, like I said, the whole process is based on trying to normalize the various layers so that one layer doesn't care about the next. So this is often done with our various components and how we build our roles. So what are our roles? Let's go look at those real quick. So I've kind of described a role, and well, I haven't really described a role. I've talked about roles as functions and elements to functions. And so one of the things to realize is roles are what we think of to do actions on nodes. It's low level, it's fairly atomic. The goal is to make it small, and then this gets to some principles that we believe in. One is composability. We believe that things should be composable. You should make small units that can be easily tested and then chained together to compose a bigger story. This allows you to, 1, validate the roles easier, and 2, it allows you to then drive and have what we call fast fail. So fast fail is a philosophy that says if something fails, we should stop immediately so that future things don't confound the error that we just incurred. That also allows us to do things like see the results. So like each of these node roles, a node role is just an instance of a role on a node. Think of it as I have a graph where the roles are the columns and the nodes are the rows. And so in this case, I have a node, and if I select one of these, I can go see what it's running. So I get real-time results, assuming it refreshes quickly. about what's going on, how it ran, its output. In this case, we were setting up packages for that system. We can see that this one was provided by a script. The script ran. We get the output of the script, and we see its success. If a failure had occurred, we could potentially go remediate that failure. For example, say it was an intermediate networking outage. We could see that a networking had failed. Then in that case, we might just choose to retry that role, and it might succeed. And then we could move on. Or if it turned out to be something we forgot to do or needed more additional configuration, we could then add that, retry it, and move forward. The idea is that it failed quickly, and we could handle that failure. Now, in this case, we can see our nodes moving through their installation. They've rebooted. They're going into the install image for CentOS 7.2. And then, let's see, get back to my deployments. In the Amazon case, it looks like we are slowly making progress through our roles. And as I mentioned before, the roles represent independent functions. So like rebar access is putting SSH keys in place so that we can access the node from various points. We rebuild the inventory so we can discover what's on it. In this case, cloud node should be pretty straightforward. And then we actually start deploying the parts needed for Kubernetes. I mentioned earlier we had our Trust Me service. Trust Me is basically our PKI infrastructure. In this case, the roles will ask for a signed certificate, ask the system to generate a new root. Then the rest of the roles can ask for, well, give me the validation for that, certificate for that. Let me put that in place. And then, oh, I need a signed cert from that root set. Let me have that and put it in place. And then all of those configurations can be injected into the downstream roles. So let's look at a couple of those roles up close. One is our K8's config role. So I mentioned attributes earlier, and I kind of described them in the context of nodes. Well, technically everything has attributes. The roles have attributes, the deployments have attributes, and nodes have attributes. And it's the combination of all those that allow us to define what should happen. So in this case, we have a whole bunch of Kubernetes options that we can configure. Now, the wizard just showed a few common ones to change, but we could actually change these before we committed it. And even if after we can commit it, we could recommit it and it would reapply those to things that we want to run, like the Docker version we're choosing to run, what version of dashboard, what's the address ranges we're going to use for the various Kubernetes components. All these configuration options get converted into parameters for Kubernetes for our roles. These are called injected attributes, and the various roles know how to process them. Now, what's a role? A role is a set of, like I said, its goal is to provide a function that we're going to operate on the node. Now, that could be provided, like I said, by Ansible, Puppet, Chef, even shell scripts. And what we do is, let me pull one up here. We'll go look at Docker, for example. It's provided by an Amazon playbook, or an Ansible playbook. The Ansible playbook runs, we inject values into the system, and that then takes action. So in this case, we can see we're going to inject some of values. Specifically, we're going to inject some proxy values so that they're available. Additionally, it will look for things like that K8's version for what Docker version it should install. And then we can see that that role lives in our tree so that we could go look at the source for that if we needed to. Now, the interesting thing is these roles we've provided, but a customer could provide their own roles, inject them into the system. We call a group of roles a bar clamp from we kind of have a tool naming convention. And a role is specified by a set of YAML files that define what roles would be and how they're going to operate. So let's go look at some of the K8's roles. In this case, they get loaded, and then you build a YAML file for them. and you can even define wizard layout. And you define your attributes that you want to have as configuration. And then you specify like a prereqs role here is going to be run by an Ansible playbook. You can map that playbook to a set of roles and a set of locations. And then you can also define dependencies. So you can say things like Docker requires that the node be installed. So in this case, right, we're saying, okay, its prereqs can only be available if should only be run if the node's installed and the network's been configured, right? All of those things can be part of it. We allow you to create various types of jigs. The jigs represent the things that are going to be run, so we can have an Ansible playbook jig, a chef jig, a puppet jig, a script jig, where you put a script into the system and it runs that. All those systems have the ability to see attributes and set attributes based upon results. So that way you can have very customized system. Now, at this point, I kind of talked about roles can create dependencies. So actually, oops, wrong thing. Let's go look at that real quick. So what DigitalRebar is doing is it's taking all those roles that you want to apply to the nodes and applying them and building this graph. And from this graph, and I'll show you the Kubernetes graph for the k8s install. And this is more for our debugging purposes, but it kind of shows what's kind of going on in that we build this graph and we start trying to walk this graph based upon what nodes can be run. And we try and do as much concurrently as possible. So in the case of Kubernetes, we're going to try and apply everything we can. And the only concurrence rules that we say is that a node can only be running one thing at a time. So in this case, I have 4 nodes in my Kubernetes install. All 4 of them should be doing something unless there's an explicit dependency. So like this is our very large graph of roles that we're operating, and we can see dependencies, like most things depend on the k8s config so that they can get valid values, that kind of stuff. But from a concurrency perspective, I can then go to my annealer view. Annealer is our term for walking this graph in kind of a continuous fashion, and we can see things that are in progress. So in this case, I have the one time we have a synchronization point is that we're bringing up etcd. So etcd is required to be up and running before any of the other system parts of Kubernetes is started. So in this case, etcd is being started, and then I have all this other items that could be run, right, on various sets of systems in the environment. And then I have all this queued work that represents roles that are blocked on something. So in the case of etcd, I can see that those values are blocked. And then some of these are part of my discovery and roles on my physical nodes. So what's happening, and if I can get to the deployment for AWS here. So once that requirement gets met, then the other roles can run, and we'll continue to make progress. So we can see kind of in the graph, in the table view, we can kind of see that all the nodes have come up, they have all their certs, and now they're waiting for etcd to start. Then they'll wait for etcd for flannel configuration to be deployed. And then we can go back to more concurrent operation. So that's the kind of concurrence and the idea around that. So at this point, I think we'll let the system kind of continue, and we'll go talk about networking. So networking. DigitalRebar provides a networking subsystem that allows us to provide a simple IPAM for our environment. We have the ability to specify the team. If you want to do a set of NICs bonded together into a team, the team mode, we can put VLANs on top of that. We can also add an additional bridge. All of that can be added to networks before installation or after, as well as in addition to networks after the admin network. So in the case of like an OpenStack deployment, you could have multiple networks that were needed post-installation. This system allows us to create a lot of those networks. We manage v4 and v6 address spaces. For the v4 space, we can create DHCP ranges as well as host ranges, and we operate kind of like a simple IPAM where the system can allocate addresses and then assign them. We also allow you to specify the router as well as a preference to indicate which network should be chosen, or which router should be chosen as the default router for each network. Additionally, our system uses a conduit, what we call a conduit system. The idea is that we try and abstract away the naming convention of the OSs, since that varies. It's ETH0 in some cases, EM1, P5, P1, whatever. And so we allow you to specify that through our own naming convention. We back that with a table that can be extended for hardware types so that you can map interfaces to our conduits. Conduits are specified like 1G0, find the first 1 gig interface and use it, or you can actually put them in pairs, in which case it'll automatically create a bond. You can do things like 10G0 and 10G1, which would say bond the first two 10 gig interfaces you find. Those all get saved as attributes on the node and then sent in, provided for the roles to use so that downstream functions don't have to have hard-coded interface names or IP addresses. They can be looked up by attribute. I think that about covers it. I'm sure I'm over my 30 minutes. So thanks for spending time learning about RackN and DigitalRebar. I hope you found this useful. For more information, please check out rackn.com or rebar.digital, and they will have you have additional information. Thank you again.